Okay, 2006, question 1. This is a KSP problem. Answer the following questions that relate to the solubility of salts of lead and barium. A saturated solution is prepared by adding excess PbI2 as to distilled water to form 1 liter of solution at 25 degrees. The concentration is found to be 1.3 times 10 to the negative, the concentration of Pb plus 2 is found to be 1.3 times 10 to the negative 3. And then, and then because of the 2 here, lead 2 iodide dissociates into lead 2 and iodine. Write the equilibrium expression. Remember, the key idea here, and this is the thing that gets students all the times, liquids and pure solids do not enter into equilibrium. So KSP, and the S stands for solubility, and the P stands for product. And I love that it's product because remember, it's right over left, but there's nothing on the left. And so what happens is it's the concentration of the lead ions times the concentration of the iodide ions squared over 1. Well, you know you don't have to do that. You don't have to put the 1. And so it ends up being, sorry, I gotta erase that. I'm going crazy. It ends up being that it's always a product. It's never a quotient. And because of this 2 goes here. And so that's the answer for 1AI. I think that's it for this page. Next question, calculate the concentration of I in the solution. Again, I cannot even tell you how many times this happens. So we get, they said that the concentration of Pb plus 2 was 1.3 times 10 to the negative 3. So basically, Pb plus 2 concentration is 1.3 times 10 to the negative 3 molar. Now here's the equation. PbI2, solid, is in equilibrium. So by the way, this is the undissolved, and then these are the dissolved. And the beauty of this problem is it's a mole ratio problem. This is a 1 to 2 mole ratio. So for every 1 mole of this, you get 1 mole of lead, but you get 2 moles of iodine because the formula tells you that these ions combine in a 1 to 2 mole ratio. And so the concentration of the iodine is 2 times 1, not, I said iodine, I meant iodide ions. And so it's 2.6 times 10 to the negative 3 molar. Calculate the value of the equilibrium constant. Well, we know from A, let me just toggle down here quick. We know from 1AI that KSP is the concentration of lead ions times the concentration of the iodide ions squared. And so this is 1.3 times 10 to the negative 3. And then this is 2.6 times 10 to the negative 3, but that has to be squared. And so if you do that on your calculator, you will get 8.788 times 10 to the negative 3. Even though this should have a unit, molarity times molarity times molarity, molarity cubed, we don't have units. And then switching colors, this has 2 sig figs and this has 2, and so we only get 2. So the best answer for this problem is 8.9 times 10, sorry, this is not negative 3, I'm sorry, it's negative 9. So it's, oops, I did that wrong. Boy, I'm having a bad time. 8.8, because this 8 means that goes up to, the 7 goes up to 8, not up to 9, times 10 to the negative 9 is the KSP. I just want to digress a little bit because a lot of times kids struggle with this problem, which is a pretty dang easy problem. Because you're used to, you know, we'd go PbI2, S, and then we'd set up an ice chart, which you often have to do. And so then, and we would go I for initial, C for change, E for equilibrium, and then M, and then M, and then M, and then this, because solids don't enter in, and then this is 0, and this is 0, and then we'd go negative S, S for solubility. Even though this doesn't participate, some of this dissolves, and so this is going to go down, even though we're not going to use it in a calculation. This is going to go up S because this is a 1-to-1 mole ratio. Some of this is going to turn over to this, but then we call this 2S, and then we get nothing here because it doesn't matter, nothing minus S. This is S, this is 2S, but then KSP ends up being S times 2S squared. And the reason why I'm taking the time to do this when it's not necessary is, remember, this 2 here gets used once here and once here. So when you have this stuff happening, just know that this 2 means that this, because of the 1-to-2 mole ratio, whatever this is going to be double, or whatever this is going to be half. And then KSP ends up being 4S cubed. And so if you know KSP and you want to solve for S, you can do it. If you know S and you want to solve for KSP, you can do it. And that's kind of what we did up here. We knew S. We knew that this was 1.3 times 10 to the negative 5. And then this is double that, so 2.6 times 10 to the negative 5. And then if you do 1.3 times 10 to the negative 5 cubed times 4, you would end up with the same thing. So there's multiple ways you can do this. A saturated, okay, and the crazy part is this is a very difficult problem, but let me draw. Remember, I'm a really bad drawer. But what happens is when you put some PbI2 into here in the solid, by the way, KSP is only for things that are that we would say were insoluble in chapter 4, and insoluble in chemistry means less than 3 grams of solute per 100 grams of solution. We say that that's insoluble, but a little bit dissolves. And what happens is some of this dissolves, and so you get Pb plus 2, and then I and I floating around in solution. And so some of it dissolves, but then when some of it runs in, it re-solidifies. And so what happens is, for KSP, you have to have a saturated solution. There has to be solid sitting on the bottom. If there isn't solid sitting in the bottom, you're not sure that the water is holding as much dissolved solid as it can. So it has to, and then, and what this KSP is true for all amounts as long as it's saturated. If it's unsaturated, all of this stuff doesn't work, because let's say you had a liter solution and you put like, you know, just one little speck, well, it all dissolved. Well, the water needs to be holding as much as it possibly can for this equilibrium to be established. So a saturated solution is prepared by forming 2 liters of solution. Who cares? This is the key word. If it's saturated, the concentrations of Pb plus 2 and I minus 2 are the same. So what are the molar concentrations of Pb plus 2 and I in the solution? Well, apparently the Pb plus 2 solution is 1.3 times 10 to the negative 5 molar, and the concentration of the iodide ions is 2.6 times 10. Sorry, not negative 5. I believe it's negative 3. Negative 3 molar. Again, I'm going too fast. I got to flip back. Yeah, it's negative 3. And so KSP is a constant as long as you don't change the temperature, and it's a saturated solution, meaning the water is holding all of it can. And the way that you know it's holding all that it can is there's some solid sitting at the bottom that's undissolved because the water is full. That will be the concentration. Now, the thing about this question is this is a question about the common ion effect, and I cannot tell you how important that is on the AP exam. And what common ion means is PbI2, sorry, PbI2 and NaI have a common ion. And so what happens is you have this saturated solution where the solid, the undissolved solid, is in equilibrium with the ions in solution. And this is set up so that the concentrations are stable. And then you open it up and you add some NaI. Well, NaI is very soluble because anything that has an alkali metal in it is soluble. And this dissociates into Na plus and I minus. And what happens is when you put some of this in, it hits the water, it turns into this. Well, now this ends up crashing to a Le Chatelier's principle. Le Chatelier's principle, which says if you have a system at equilibrium and you stress the equilibrium by changing the conditions in such way, the equilibrium will shift to reduce that stress and the equilibrium will be reestablished. And what happens is, and it's equilibrium constant, I'll go back to the same ratio, just that right after you put it in, what happens? Well, what happens is you added some I minus. It doesn't like that you added I minus. It tries to get rid of it by shifting to the left, because the way to get rid of the I minus is to speed up this backward reaction and convert it over to PbI2. That's what gets rid of it. Well, if it shifts to the left, that means you have more PbI2, because that's on the left, and less Pb plus 2. In other words, you have more insoluble salt if it shifts less, and you have less dissolved ions. Now, it's hard to say about the I because it doesn't even tell you how much you put in. So usually you don't talk about the thing that you're changing. And so the question is, does the molar concentration of Pb plus 2 in the solution increase, decrease, or remain the same? Justify your answer. And so the Pb plus 2 concentration decreases. And all of this is justification. The fact that you're going to use Le Chatelier's principle, you're going to added I2 causes the equilibrium to shift to the left, which means more PbI2 solid, less Pb plus 2. Okay, this is a really hard problem. So very, very, very important, and I'm not sure that you did this last year. So basically, the first thing I'm going to do is we have, okay, so the value of the KSP for BaCrO4. So basically, I'm going to go down to part 2 because this is interesting. The KSP for barium chromate is 1.2 times 10 to the negative 10. It's a tiny number. Why that's important is if you calculate Q, which is what we call KSP when you're not sure if you're at equilibrium, and Q is bigger than 1.2 times 10 to the negative 10, that means you'll see a precipitate. Because a precipitate actually just means that you have undissolved solid sitting at the bottom, if you let it sit there long enough, and you can be sure that the solution is saturated. And that doesn't happen until you get above this threshold. Now, the other thing is, if Q is smaller than 1.2 times 10 to the negative 10, you will have no precipitate because you won't have enough ions in solution to make a saturated solution. So, solution is unsaturated. Okay, so keeping in mind, the way that we have to do this problem is we need to figure out what the barium ion concentration is, and then we need to figure out what the chromate ion concentration is, And then we are going to multiply them together because KSP is the concentration of the barium to times the concentration of the chromate, because barium chromate is not very soluble. A little bit dissolves and you get this, and so you can see that. And because barium is +2 and chromate is -2, these combine in a 1-to-1 mole ratio, which makes the problem much less difficult than it could be. And so we're going to calculate this, and we're going to calculate this, and then we're going to multiply them together. And if it's bigger than this number, we're going to say, oh, and we're going to show why a precipitate does not form. Here's the little hint. When we're all done, Q must be less than 1.2 times 10 to the -10, because we're supposed to show why a precipitate does not form. Now, we're going to come up here, and remember, this is the crazy part, is whenever you add two solutions together. Okay, I'm going to erase this. What happens is, because when you add 500 milliliters and 500 milliliters, you are changing the volume, and it changes the concentration. So what I'm going to do here is, and again, keep in mind, this is a very difficult problem. Barium nitrate. Barium nitrate. The concentration of that is, I love these problems because I know that moles per liter times liters will always give me moles. So what I'm going to do first here, and actually it's really kind of sweet, because if you notice, they were kind enough here to make these numbers the same and these volumes the same. And so what happens is, if I take 8.2 times 10 to the -6 moles per liter, because that's what molarity means, and multiply by 0.500 liters, because that's what 500 milliliters is, we end up with 4.1, because I'm going to take half of 8.2 times 10 to the -6 moles. And then the new volume is 500 milliliters plus 500 milliliters, which is 1,000 milliliters, which is 1 liter. And so this ends up being 4.1 times 10 to the -6 molar. Now that's crazy. That's barium nitrate. But remember, when barium nitrate dissociates, it dissociates into barium ions and 2 nitrate ions. But this is a 1-to-1 mole ratio. So not only is this the concentration of the barium nitrate, it's also the concentration of the barium. And the exact same calculation can be done for this, because sodium chromate dissociates into 2 sodium ions because of this, but 1 chromate ion, and this is a 1, and this is a 1. So, and this is the same, and this is the same, and this is the same, and this is the same. And so what you need to know is the concentration of the barium and the concentration of the chromate after you mix them together gets cut in half, because you have twice as much volume, and so it gets cut in half. So now we're supposed to use the molar concentrations from part A, which is each of those is 4.1 times 10 to the -6, to show why a precipitate does not form. And so what happens is, and because we're not sure we're at equilibrium, Q, which is the same thing as, let's do purple just for fun. Q is what you call KSP if you're not sure you're at equilibrium. For barium chromate is this. And so what happens is, we learned in question up here in I that this was 4.1 times 10 to the -6 molar. And this is 4.1 times 10 to the -6 molar. And remember, Q and K are unitless. And if you do that, you end up with, and this has 2 sig figs and this has 2 sig figs, so 1.7 times 10 to the negative 11. And you can see that Q is less than KSP because negative 11 is smaller than negative 10. So let me just extend this. So no precipitate will form. So another way to do that problem is to use this equation. M1V1 equals M2V2. I'm going back up to I. So the new molarity is the old molarity, which was 4.2 times 10 to the negative, now what was it? Sorry, I'm going to go back. Now I'm going to go forward. 8.2 times 10 to the negative 6. Okay, so then I got to grab the eraser. So then M2 is equal to M1 V1 over V2. And so this was 8.2 times 10 to the negative 6 molar. And then this was 500 milliliters. And this was 1,000 milliliters. And when you do that, you get 4.1 times 10 to the negative 6. You could also use that equation to get these concentrations. I just am a big fan of anytime I see moles per liter times liters, I want to get moles. And then I'll get the moles and divide by the new liter. But either way, you get the same answer.